All right, so let's start. Today you are going to learn about chapter 4, and chapter 4 is about force and Newton's laws of motion, and this is part of dynamics. Okay. All right, so in chapter 2 and chapter 3 you learn about kinematics. Kinematics tells us how objects move, and here in dynamics you are going to learn about why objects move. Okay, and the first example you are going to learn is the force. Okay, so let's start to learn about force. Okay, so what is force? So the simple definition of force is it is a push or pull. Okay, so here you see that we have a spherical object. Okay, so this is the spherical object, and we have a push. I mean, we can push it, we can pull it. Okay, so pushing or pulling means applying force on this object. Okay, now here you can push this spherical object in this direction, you can push it in this direction, and you can push it in this direction. Okay, so depending on the direction the effect will be different. Okay, so I mean, from our everyday experience we can basically relate these, right? So what it means force depends on the direction. Okay, and if you remember from the definition of a vector quantity, you probably already remember that vector means to describe a vector quantity we need both magnitude and direction. Okay, so here you see that to describe force, yeah, magnitude is important, and at the same time the direction is also important, right? So because the direction is important, force is a vector quantity. Okay, so remember that. Now the standard international unit for force is newtons, and we use capital N to represent newtons. Okay, and later in this chapter you will see that Newton is related to the kilogram and meter per second square. And if you remember, kilogram is the unit of mass, and meter per second square is unit of acceleration. So later you will see that force is related to mass and acceleration by this equation. Okay, and because force is a vector quantity, we normally use this symbol. Okay, force, and then an arrow on top of it to represent that it is a vector quantity. Okay, so this equation will be something like this. Okay, force equal to mass and acceleration. Acceleration is a vector quantity, so we have to use an arrow on top of it. All right. Next is the net force. So to represent net force, we either use net explicitly or sum. Okay, but what is net force? So to understand this, let's go to this simulation. Okay, so here you see that when we have only one robot, okay, then the net force is basically the sum of forces. Okay, so here you see that the sum of forces equal to the force the robot is applying, because there is only one force, so the sum of force is basically the same as the applied force. Okay, applied force by this red robot. Okay, now if I add one more robot here, so you will see that this robot, the bigger one applied 150, the smaller one applied 100 Newton. So now the net force, or the sum of forces, is 250 Newton, and because both forces direction are to the right, so the net forces direction is also to the right. Okay, the same thing if we have this robot which which applied 150 to the left. Okay, then the sum of force is just 150 to the left. Now another one. Okay, so this one applied 150 and this one applied 100, so 150 and 100 is 250, and because both forces directions are to the left, the sum of force is also to the left. Okay, all right, now what happen if we have one is in this direction, one is in this direction. Okay, so you see that the red one is applying 150 to the right and the blue one is applying 150 to the left. So 150 minus 150. Okay, so here this is plus 150 because it is to the positive x direction, and this is 150. So 150 and 150, I mean positive and negative cancel out, so the sum of forces is equal to 0. Okay, so this is basically the net force. Okay, so net force is basically the sum of forces. So mathematically we use F net, or this is the summation symbol. If you have already taken a math course, you probably already know this is the sum symbol. Okay, so either we use this one or this one. Okay, so for example, now in this situation, the net force is equal to 0. All right, now what happens if the net force is equal to 0? So if net force is equal to 0, there will be no change in the object motion. So here this is at rest, you will see this is the object is at rest. Okay, even there are individual forces acting on this object, but there is no change in the motion. Okay, now if we have net force that is not equal to 0, so for example here, now to the left we have 150, and to the right we have 200 Newton. So plus 200 Newton and then minus 150 Newton. Okay, so the net force is plus 50 Newton. Plus 50 Newton means to the right. So now, because now the net force is not equal to 0, the sum of forces is equal to 50 Newton, we expect some motion. So let's see. So you see that there is motion in the direction of the net force. Okay, all right. All right, so this picture basically tells the same thing. Okay, what we see in the simulation. So here you see that when the 2 Newton and 2 Newton, and the same forces applied in two different directions, in opposite direction, the net force will be equal to 0. When two forces acting both are in the same direction, the net force is, you have to add them to get the net force. When they're in the different direction, you have to subtract them. And here, because we have negative 2 Newton and positive 3 Newton, the net force is positive 1 Newton. So the direction is to the positive x-axis. Okay, so that's how net force works. All right. The next thing we are going to learn is Newton's laws of motion. And it basically describes the relation between the force and motion. Okay, so in the simulation, you already see that when net force equal to 0, there is no motion on the object. Right? When net force is not equal to 0, the object moves. Okay, in the same direction of the net force. So Newton laws of motion basically tell about that. Okay, so we have 3 laws: first law, second law, and third law. Okay, so let's see what is the first law of motion. Okay, so let me first read it and then explain it. Okay, first law of motion tells us that if the net force on an object is zero, the object originally at rest remains at rest, and the object originally in motion in a straight line at a constant speed remain in motion in a straight line with constant speed. Okay, so what it means? So it has two parts. I mean, it says that if net force on the object is zero, okay, then the first part is says that uh, the object originally at rest remains at rest. So this is the first part. So when net force equal to zero, if the object is at rest, originally at rest, it remains at rest. Okay, and it's easy to understand. Okay, let's say we have this soccer ball here, it's at rest. If the net force is equal to zero, I mean, if there is no force or net force equal to zero, net force means, let's say we have forces from this direction and forces from this direction, but the sum of the forces, if the sum of the forces equal to zero, then there will be no change of it. Okay, and it's easy to understand. Let's say we have a textbook on the table, okay, that is at rest. Okay, if no one apply any force, okay, on the textbook, it will be on the table forever. Okay, so that's basically the first part. Now the second part tells us that if the net force is equal to zero, okay, the object originally in motion in a straight line at constant speed remains in motion in a straight line with constant speed. Okay, so it says that if the net force acting on this object is equal to zero, and if it is moving in this direction at a constant speed, it will be keep moving in this direction at constant speed. Okay, but I mean, from our experience of our everyday life, it's not that, right? If an object is moving in this direction, okay, at constant speed, at some point it will stop, right? Why it stops? If I mean, even we do not apply some explicit forces, the nature has applied some forces on the object. Okay, so here, if it is moving in this direction, if the ball is moving in this direction, there is something called friction force between the ball and ground. There is air resistance. Okay, is another kind of friction force. Okay, so both are friction. So even we are not applying explicit force on this object, but the nature is applying some forces. Okay, so so that means net force is not equal to zero. Okay, so there is some net force by friction and air resistance. So that's why when an object is moving at a constant speed in a straight line, it is not keep moving. Okay, it stops at some point. Okay, so what it means in our everyday life, because of the friction and air resistance, it's difficult to prove the second part. Okay, but I mean, we can prove it using the simulation. Okay, the simulation I showed earlier, we can use to prove it, because in that simulation we have the option to turn on and off the friction. Okay, so if we turn off the friction, okay, then you will see that. So let me turn off the friction. Okay, so if we turn off the friction, you will see that we can prove that. Okay, so the object's mass is, so here we have a box, its mass is 50 kilogram. Now there is no force applying, I mean, no one is applying any force. Okay, so we have robot, it can apply some force. So let me apply 10 Newton. Okay, so you see that robot is applying 10 Newton of force. Okay, and the object is moving, because the net force here is just the 10 Newton to the right. So because it is to the right, I mean, we expect a motion to the right, and it's happening. Okay, and you see that the speed is increasing. Okay, now let's say let's try to prove the Newton's first law, the second part. So to do that, let me remove the forces. So now the net force, the sum of force is equal to 0. Okay, so you see that even the net force is equal to 0, the object is moving to the right. Okay, because it was moving to the right, it will keep moving in the same direction at constant speed. So the speedometer here, you see that it shows a constant speed. Okay, the speedometer shows that it is moving in a straight line at constant speed. Okay, and that you can prove because here the friction is equal to 0. Okay, so if you consider the friction, okay, between the box and the ground and the air resistance, at some point it will stop. But here, because it is a simulation and we turn off the friction and the air resistance, it will be keep moving unless you stop it. Okay, all right, so that's basically the first law of motion. Now let's try to understand the other thing. Okay, all right. So the Newton's first law of motion is also called the law of inertia, because by definition, inertia is the object's tendency to maintain its original state of motion. And Newton's first law of motion is also says the same thing. Okay, so if an object is at rest, initially at rest, it wants to stay at rest. If it is in motion, it wants to stay in motion. Okay, so because of this, we call it sometimes we call it law of inertia. All right, so here we have two examples. Let me skip it. Okay, so the next thing I'm going to discuss is mass. Okay, mass is the measure of the inertia. Okay, or we can say that it is the material content of an object. Okay, and it's okay, it basically tells us how much material we have in any object. Okay, the material content, and this content is constant. Even if you bring this in some other planet, there will be no change of the material content. Okay, so that's why it's a scalar quantity. It does not depend on where it is. Okay, it's basically the material contents. It's a scalar quantity, and we use symbol m to represent mass, and it's a scalar quantity, and the standard international unit for mass is kilogram, and we use kg to represent mass. Okay, so mass is basically the material content of an object. Okay, it's a scalar quantity. We use kilogram. The kilogram is kilogram, or kg is basically the standard international unit for mass. Okay, and small m is used to represent mass. Okay, all right. The next thing is the weight. Okay, mass is not weight. Okay, so mass is a property of an object. On the other hand, weight is the force exerted on that object by gravity. So sometimes we call this as gravitational force, or the force of gravity. Okay, so force of gravity and the weight of an object is the same thing. Okay, or gravitational force or force of gravity. So the mass is the material content, and weight or the gravitational force is just a force. Okay, so do not confuse weight and mass. Although in everyday life we use we interchangeably use mass and weight. For example, if you go to a doctor, okay, doctor basically measure, or the nurse basically measure the mass, your mass, but she probably say your weight is this much. Okay, so although we use mass and weight interchangeably in physics, mass and weight are two different things. Okay, mass is the material content. Okay, how much material you have in your body. Okay, on the other hand, the weight is a force. Okay, it's a gravitational force, the force that exert on you by the gravity. Okay, so because weight is a force, and because force is a vector quantity, weight is also a vector quantity. Okay, so we will see later in details about it. Okay. All right, so here we have I put a cartoon. Let me know if you understand this. All right, now weight basically depends on the gravitational acceleration. Okay, mass does not depend. So mass, okay, so mass m is always same, no matter whether you are in Earth, okay, or in Moon, the mass will be same mass, okay, but the weight or the gravitational force will be different. So for example, gravitational force will be 1/6. So the gravitational force of an object at Moon will be 1/6 of the gravitational force at Earth. Okay, so that's because the gravitational acceleration here is about 10 meter per second square. I mean 9.8 meter per second square on Earth. On the Moon, it is 1.70 meter per second square. Okay, it's 1/6. Okay, because the gravitational acceleration is higher on Earth, the gravitational force or the weight of an object is higher on Earth. Okay, because the gravitational acceleration is lower on the Moon, the gravitational weight is also be lower on the Moon. Okay, so remember that. Okay, we are going to formally define the gravitational force in the next slide or the following slide. All right. So to do that, we first need to understand the Newton's second law. Okay, so to get a formal definition of the gravitational force, first we need to understand Newton's second law of motion. Okay, so the first law, so let me recall what is first law and then let me come back to Newton's second law. Okay, so Newton's first law tells us that when net force is equal to 0, the object initially at rest wants to stay at rest. If the object is initially in motion at constant speed in a straight line, it wants to be in motion at constant speed in a straight line. So that is the Newton's first law. So what is the Newton's second law? So Newton's first law basically tells us about when net force is equal to 0. On the other hand, Newton's second law tells us when net force is not equal to 0. Okay, so first we learn about when net force is equal to 0. Now we are going to learn when net force is not equal to 0. Okay, so if net force is not equal to 0, then we already know that object will be in motion, right? So let's try to understand in details. Okay, so to understand this, let's consider these three picture. Okay, so now let's say the net force is not equal to 0. So here I'm just showing this force, and this force means net force. Okay, that is not equal to 0, and this is the object. Okay, I mean basically the whole thing is the object. So if net force is not equal to 0, let's say it was at rest. Okay, rest means v equal to 0. I mean initial v 0 equal to 0. So because of this force, the object starts moving. That means it has some final velocity, right? When you apply this force, initially the velocity was equal to 0. Because of this force, now the velocity is some non-zero. Okay, velocity has some value. So what it means velocity changes, so from 0 to some non-zero value, right? So when velocity change means delta v, right, in some time, what it means it has some acceleration, right? So when you apply some force on an object, it accelerates, it changes velocity, right? So a common very popular example is when you start your car. Okay, I mean, when you start moving your car, I mean, you start your car, and then when you start your start moving your car, that means you are accelerating, right? So you accelerate your car. So you accelerate your car means you are basically changing your velocity. So initially it was at rest, right? Because you accelerate it, that's why it starts moving, right? That means you are applying some force. Because of this force, your car accelerate, and accelerate means you are changing the car's velocity, initially at rest, and at some point it is at some non-zero values. Okay, so it's the same thing happening here. When you apply a force on this object, the object was initially at rest. Now because of this force, it gets some velocity, some non-zero velocity. So you see that velocity changes, and change in velocity means acceleration. Okay, so the summary of this is, when we apply a force, the object accelerates. Okay, so that means there is a connection between force and acceleration, right? Now here you see that. Now let's consider this picture and this second picture. Okay, here you see that this force, because of this force we have this acceleration. Now we increase the force, you see that the acceleration is also increases. Okay, so that means force and accelerations are proportional to each other. Okay, so we can write A is proportional to the net force. Okay, so net force is the sum of the forces. Okay, so you see that in these two pictures, if you compare the first and second picture, you can see that, right? When you increase the force, the acceleration will also increase. When you decrease the force, the acceleration will decrease. Okay, so that means acceleration and the net force are proportional to each other. All right, so this is the first relation. And okay, so the first relation is here. Okay, now the second relation, to understand the second relation, we have to compare the first picture with the third picture. Okay, so now in this case, okay, so we already know what is going on here. So we apply a net force, okay, which is not equal to 0. So because of this force, the object accelerates. Okay, and we already know that more the forces, more the acceleration. Okay, now what happened if we do not change the net force? Okay, so the net force we did not change here. Okay, you see that the length of the arrows are the same in both cases, but we change the masses. So here we had only one box. Now we have more boxes, 6 boxes. Okay, so that means we have more mass here. Okay, so you see that the same force here and here, but here we have less mass, here we have more mass. Okay, so what happened here? So when we have more mass with the same force, the acceleration is small. So here you see in the third picture, the acceleration is small. Okay, so what it means? It means more mass means small acceleration. Okay, so more force means more acceleration, more mass means less acceleration. That means acceleration is inversely proportional to mass. Okay, the more the mass, less the acceleration, less the mass, more the acceleration. Okay, so this is the second relation. So the first relation is acceleration is proportional to the net force. Second relation is acceleration is inversely proportional to the mass. Okay, now if we understand these two things, let's combine these two to get one relation. Okay, so if we combine these two, we get something like this. Okay, we get something like this. So A is equal to F over m. Okay, so this is our relation. When we combine these two equations, we get this. And now now we can simplify one more time to write the equation as something like this: F equal to ma. I mean, if you multiply both sides of this equation by m, you get F equal to ma. So this is basically the Newton's, basically Newton's second law of motion. I mean, both are used, either this one or this one. Okay, both are used for Newton's second law. Now you see that in the first slide we use this equation, and I told you that Newton is connected with kilogram and meter per second square. So this is the equation. Okay, all right. So because the force and acceleration both are vector quantities, so the correct form of this equation is this one. Okay, so this one, the force vector equal to the mass is a scalar times the acceleration vector. Okay, so this is the correct form, but this is the vector form. But you know that when you solve problem, we cannot use we can use, but using the vector form is difficult when you do some problem. So what we do, we basically break this vector into its x and y component. Okay, so I mean, it will be easier if we it will be easier to solve a problem when we break the Newton's second law into its component. Okay, so what it means, in component form, the x component is this one, y component is this one. So fx, okay, equal to max, and fy equal to may. Okay, so what it means, in any problem, okay, so let's say we have an object. Okay, let's say we have one force is in this direction, one force is in this direction, and let's say we have one force is in this direction, one force is in this direction. Okay, let me call it F1, F2, let me call it F3 and F4. Okay, so we have to treat F3 and F4 together, so they are the y component forces, and F2 and F1 together because they are the x component forces. Okay, so the similarly for acceleration, we cannot combine acceleration along the x direction to the acceleration along the y direction, so we have to be careful. Okay, so we'll be doing some problem, and hopefully that will make the concept more clear. Okay, but for the time being here, just remember that we have two components. Okay, so for the x component, the equation is something like this. For the y component, the equation is something like this. And because m is a scalar quantity, there is no change here. So here you see, in both cases we use m, but because force and acceleration both are a vector quantity, so we have to, in equation, we have to use x with x, y with y. Okay, so we'll do some problem, don't worry. All right, now let's try to understand the gravitational force or the weight. So for the gravitational force, we use this symbol, F subscript G, to represent that it is a gravitational force, or W. Okay, so both are the same thing. Okay, W means the weight. So the gravitational force or the force of gravity or the weight are all the same thing. We use either this symbol or this symbol, W for the weight, and F subscript G means the gravitational force. Okay, so if you see this or this, it means they are either gravitational force or weight, which has the same meaning. Okay, Now, what is the relation between, what is the mathematical definition of the gravitational force? Okay, so to understand that, we have to start from this equation, F equal to ma. Okay, now let's replace a, the acceleration. So a is the acceleration by gravitational acceleration, right? So z, this is the gravitational acceleration or acceleration due to gravity, right? So in this equation, in the Newton's second law, if I change a by the gravitational acceleration, we have to change the left hand side with the gravitational force. Okay, so the gravitational force is this. Okay, so the definition of gravitational force is equal to m times the gravitational acceleration. So W is also equal to m times the gravitational acceleration. Okay, now, yeah, so we, in vector form, it's something like this. Now, you know that the gravitational acceleration is always downward, right? Because Earth pulls everything downward, right? So because the direction of the gravitational acceleration is always downward, okay, the gravitational force's direction is also downward. Okay, so this force, you see that direction is downward. So remember that it's a special force. Okay, and we already know that the direction of the gravitational force is downward, and it's always downward. Okay, all right. The next force is the normal force. Okay, for the normal force, we use either F subscript n for the normal or just n for the normal force. Okay, so both are used. So if you see F subscript n or just n, for both I mean the normal force. Okay, so what is the normal force? So to understand this, let's say we have an object on the table. Okay, let's say this is the table, and let's say this is the object. Okay, and let's say this object has mass m. Okay, so if an object has mass, it always has gravitational acceleration, and it is always downward. So the gravitational acceleration is mg, right? So this is the gravitational acceleration. Now, so if we have only one this force, and if it is downward, we expect the object move downward, right? Because the Newton's second law tells us that if the net force is not equal to 0, right? If the net force is not equal to 0, the object will be moving in the same direction of the net force. So if there is only force acting on this object on the table, then we expect the object moving in this direction, right? But it is not moving, right? We already know from our everyday life, we already know that when an object is on the table, it stays on the table. That means something is balancing the gravitational force, right? So that means the table is exerting some force on the object. Okay, that's why that force is balanced and the net force is equal to 0. Okay, because here the object is not moving, that means table is exerting some force on this object, and that force is the normal force. Okay, so here you see that this is the same picture. We have the textbook. The gravitational force is downward because the textbook is not moving downward. So that means the net force is somehow 0. Okay, so how the net force is equal to 0? Net force is equal to 0 because the table is exerting an equal and opposite amount of force to balance the gravitational force. Okay, All right. Now, few things to remember for the normal force is normal means the perpendicular. So in mathematics, normal means perpendicular. Okay. So that means normal force is always perpendicular to the surface. So if we have surface something like this, and if the object is on this surface, the normal force will be in this direction, and then the angle is 90 degree. Angle 90 degree means it is perpendicular to the surface. Okay, so if the object is here, somewhere here in a tilted or inclined plane, okay, then the normal force will be in this direction. Okay, and you see that this is perpendicular to the surface, that means this angle is 90 degree. So normal means perpendicular. When an object on a surface, okay, normal force will be perpendicular to that surface. Okay, so normal, we'll have normal force when the object is on some surface. Okay, so if the object is not on some surface, there will be no normal force, there will be some other forces. It's a normal force is basically a contact force between the object and the surface. Okay, so if the object is somewhere here, then we have normal force. If the object is hanging, okay, from the ceiling, there will be no normal force, because there is no on the bottom of this object, there is no surface. Okay, so if the object, if an object is on some surface, then there will be normal force. If there is no surface, there will be no normal force, and normal force is always perpendicular to the surface. So flat surface, it will be something like this. For inclined surface, it will be something like this. Okay, so remember that. All right, now for some cases, the normal force is equal to the gravitational force. For example, for this simple problem, okay, the gravitational force and the normal force are equal and opposite, but it's not always the case. Okay, so here, because the object is at rest, okay, the normal force and weight, they are equal and opposite, because they balance each other. Okay, so let's say if there is another force here acting, let's say you push a force, you push or you apply a force on this textbook. Okay, some other external force is applying on this object, then the normal force and weight are not equal. Okay, so normal force and weight are equal and opposite to each other when there is no other force other than the normal force and the weight. If there is other force acting on this object, then it will be different. Okay, so we will be doing at least one problem explaining this in the next lecture. All right, but for the simple case, normal force and weight are equal and opposite to each other, but it is not always the case. All right, now let's try to understand the third law, Newton's third law of motion. And it's very simple. It tells us that every action has its equal and opposite reaction. Okay, what it means? It means whenever one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first. Okay, so to understand this, let's consider these two pictures. So the Newton's third law tells us that when this person applies 100 Newton to this wall, okay, so this person is applying a force in this direction. So Newton's third law tells us this wall exerts exactly 100 Newton force to this person in this direction. Okay, so one object, here the person is applying 100 Newton here in this direction, and the wall is applying 100 Newton in this direction. So every action, so here one is action force, another is reaction force. So action force by the person is 100 Newton to the right, and reaction force is 100 Newton again. I mean, it should be equal, okay, but in the opposite direction, to the left. Okay. All right. So here is another example. So this lady is applying 100, some force to the wall, okay, in this direction, and the wall is applying some force in this direction. I mean, wall is applying the same force to this lady in the opposite direction. So that means this direction, okay? And you know that lady is applying this force, applying a force in this direction to the wall, okay? If wall does not apply the same amount of force in this direction, then there will be no motion for this lady, because the lady is moving in this direction, right? Because the lady is moving in this direction, so that means there is some net force in this direction. Net force's direction will be this, okay? So how she get this net force? So she get this net force from the wall. She's applying force in this direction, right? So if she does not get back the reaction force, she cannot go to, I mean, she cannot move forward, okay? So remember that. So she's applying a force on the wall, okay, and wall is giving back the same amount of force in the opposite direction, and because of the force exerted on her by the wall, she's moving forward, okay? So interesting. So she's applying force, that is the action force, and she's moving forward because of the reaction force from the wall to her, okay? Now okay, so many students make mistake understanding the Newton's third law and some other things. For example, the mistake with this one, I mean, this normal force and the weight, that many students think that the normal force and weight are the action reaction pair of the Newton's third law, okay? So to avoid this confusion, let me make a statement, okay, and then come back to here. So the statement is, okay, this one: the forces, I mean the action reaction pair forces are exerted on two different objects, okay? So for example, here here you see this is one object, this is another object, the lady is one object, the wall is another object. So action reaction pair are acting on two different objects, okay? So when we talk about Newton's third law, then remember that we are talking about two different objects, okay? The forces, one object is exerting force on another object, and the second object exert the same amount of force on the first object but in the opposite direction, okay? So that is the Newton's third law, okay? The two different objects, but in the weight and normal force, the both are exerting on same object, the textbook. So for example, if I go back to this one, so here you see that the textbook is the object, and both normal force and the gravity are acting on the textbook, okay? And of course there are, I mean, we can we can use the concept of the third law here, but I don't want to do that, okay? So yeah, there, because the textbook is exerting some force on the table, okay, and the table is exerting the normal force. So that are the, I mean, we can think that the table and the textbook are the two different objects, and then we can have the two different forces of action reaction pair, okay? But the normal force and weight here are both exerting on the same object, so they are not the the action reaction pair of Newton's third law. Okay, so here yeah, so here you can see that this is basically the same thing. This is a statue. There's the statue. When we have a statue, when we have an object, we have the gravitational force downward, and then because it is at rest, we have the normal force here. Okay, so it's basically the same thing. So this is the gravitational force, and this is the normal force. Okay, so these both exerting on the same object, on the statue. Okay, so they are not the action reaction pair. Okay, not the second, not the third law, Newton's third law. But here we can do the Newton's third law. Okay, so here you see that the gravitational force is there. This is the normal force, both exerting on the same object, but this one is exerted by the table, okay, on the statue. So the statue exerts some force on the table. Okay, so F prime N. Okay, so these two forces basically are the action reaction pair. Okay, so here you see these two forces are action reaction pair, but do not confuse this force and this force with this force and this force. Okay, so the action reaction pair means we should have two different objects. Okay, on the other hand, normal force and gravitational force both are exerting on the same object. Okay, all right. All right, so rocket propulsion is another example of Newton's third law. So so here you see that the hot gases from combustion spew out of the tail, okay, of the rocket at high speed. Okay, so one is I mean the hot gases are going in this direction, so they're pushing on the air, and the air push the rocket on this direction, and that's why the rocket goes upward. Okay, there are many other examples of Newton's third law in our everyday life. All right, so the next thing is free body diagram. Okay, it's very important. So free body diagram is very important when you solve dynamics problem. I mean a problem related to force. It's very useful to first draw a free body diagram and then solve the problem. Okay, so if you first draw the free body diagram and then solve the problem, it will be easier. Okay, so what is the free body diagram? Okay, a free body diagram represents the object as a particle and shows all of the forces that act on the object. Okay, so there are some rule we have to follow when we draw a free body diagram. Okay, so here I summarize it, and then let me explain what I mean by the free body diagram. Okay, so in a free body diagram, we have to identify all the forces that act on an object. Okay, so whenever we have a problem, okay, by reading the problem, we have to understand that what forces acting on this object, I mean on the object of our interest. Okay, there may be two different objects. Okay, so if we have more than one object, then we have to draw separately for each object. We have to draw a free body diagram separately for each object. Okay, all right, so once you know all the forces, once we identify all the forces acting on the object, then you have to choose a coordinate system. Okay, so normal coordinate system is this one, right? So this is x, this is y, right? So normally we use this coordinate system. Sometime when the object on an inclined plane, okay, something like this, then we probably use a different coordinate system. Okay, so the y-axis in this direction and x-axis is in this direction, or x-axis is in this direction. Okay, so when we have something like this, we use different coordinate system, but normally we use a coordinate system something like this. I mean that is our our usual coordinate system. Okay. All right. So once you choose your coordinate system, once you are happy with the coordinate system and you already identified the forces that acts on an object, the next thing is to put the object at the center of the coordinate system. Okay. Okay, so the represent the object as a dot. So here you see the represent the object as a dot at the origin of the coordinate axis. This is the particle model. Okay. And then draw the vectors. Okay, and then draw vectors representing each of the identified forces. Okay, draw and label the net acceleration vector. Draw this vector beside the diagram. Okay, so it's basically a mistake, beside the diagram, not on the particle. Okay, so let's try to understand this free body diagram for this example. Okay, so the free body diagram concept for this problem. Okay, so here we have an object. Someone is applying this force, pulling this object by 400 Newton. Okay. All right. So the first thing is draw a coordinate system. So this is a coordinate system we are going to use. Okay. Okay. So this is the coordinate system, or regular. Okay. So this is Y, this is X. The first thing is, this is our object at the center of the coordinate system. Now let's try to understand what force or forces acting on this object. Okay, the object has mass, so it should have a gravitational force. So this is the gravitational force, mg. Okay, because the object is on the surface, there should be a normal force. Okay, normal force. Now this is the applied force, pulling force. Okay, and that is making an angle 30 degree with the positive x-axis. Okay, now the problem here, I mean, this is basically the free body diagram, but the problem is when a force is not along the x-axis or along the y-axis, I mean not along the x or y-axis, we cannot use these. So for example, this fp, we cannot use this in our equation. Okay, because the equation is fx equal to max, right? If you remember from the Newton's second law, and fy equal to may. So we cannot use this force, I mean for this or this. Okay, so whenever we have a force that is not along the x-axis or y-axis, the first thing we have to do is break that vector into its component. And we already know how to break it, right? You already learned it in chapter 3, right? So how to break it? So to do that, okay, so to do that, so we normally draw a perpendicular line on the horizontal axis, or horizontal axis. Okay, so and this is because this is parallel to the y-axis. This is our y component, I mean fpy, and this is fpx. Okay, all right. So when the bottom line here is, first we have to identify all the forces on the object and then draw the arrows. But if there is a force that is not either along the y-axis or the x-axis, then you have to break it. Okay, so break it by using the analytical method that you already learned in chapter 3. Okay, and then the last thing is what is the direction of the acceleration. So the direction of the acceleration here, you know that when you pull this box in this direction, there will be acceleration only in this direction. There will be no acceleration in this direction, right? So the acceleration direction we have to also draw. So the acceleration will be A, and it will be in this direction. So you can also call it AX to basically show that there is only acceleration along the x direction, and there will be no acceleration along the y direction. Okay, so once you have that, then you are done. Okay, done in that sense that in that sense that now you can write these two equations, fx equal to max and fy equal to may, and solve the problem. Okay, all right, so let me summarize this one again, and then that's it for today. Okay, so the first thing, when we have a problem, something like this, we have to understand that, I mean, we have to identify all the forces that acting on this object. So here we have the gravity, we have the normal force, and we have this force. Okay, but this is not useful because this is neither along the x-axis or the y-axis. So if we have something like that, we have to break it into its component. And how to do it? How to break a component? So whenever we have this, we have to draw a perpendicular line from the tip of this vector. Okay, and that is parallel to the y-axis most of the cases. So this is fpy, and this will be fpx. Okay, and you know that how to do it. Py is opposite, so it will be fp sine theta, and px is adjacent, so it will be fp cosine theta. Okay, so now you have all the forces you identified, right? You have normal force, you have the gravitational force, you have fp sine theta and fp cosine theta. And then you have to understand that when you pull this box in this direction, there will be only acceleration that will be in this direction. Okay, so you have to also draw acceleration to show that the object is moving in this direction. Okay, all right, so once you have that, then we have to separately write two equations. One is fx equal to max, and then another is fy equal to may. Okay, and then solve the problem. So we'll be doing some problem in the problem solving lecture. Okay, hopefully that will make this concept more clear. Okay, so I am going to stop today here. So I will talk more about some other forces in the next lecture.